All right, hello, welcome back again. So now we're gonna go into a little bit more detail as far as summarizing what we kind of shared our ideas about energy conservation, summarizing it in a more concrete way mathematically. So going deeper into the energy interaction model, and I'm gonna introduce this idea of diagrams, which will help us represent some kind of interaction that happens, that occurs, that causes changes in energy of our system. Okay, and why do we want to do this? Well, there are several questions that we're gonna want to ask. For example, how much energy does it take to melt 1 kilogram of ice? So what do you think that will depend on? Well, um, kind of intuitively, it should depend on how much ice we have. If we had 10 kilograms versus 1 kilogram, then most likely that should require more energy. Also, the fact that it's ice versus another material. What if we're melting solid gold? Would that require a same amount of energy even if we had the same amount? So we will look at, does it depend on the material, the amount? Also, we will look at systems where two separate substances are interacting. So for example, if you have some lemonade, warm lemonade that you mix with ice and you put it in a thermal container and you close it, what will be the final temperature of this mixture after some time? Will all the ice melt? What do you think that will depend on? Well, intuitively, it will depend on, how warm was that lemonade that you started with, and with how much ice did you put in, and so on. Another example of a question: if we boil water in a kettle for 10 minutes, will any water evaporate? So what is the time? How does the time matter? Well, the time will tell us how much energy we put in, because the more time passes, the more energy is being added as we boil water in a particular kettle. So we'll look at all these different concepts. Eventually, we'll start getting more and more mathematical about our treatment of conservation energy, but at this point, we're still being rather kind of conceptual, because that's always the first step of understanding things. Is let's think about concepts. How do they make sense? How do we apply them? And before we kind of jump into using the equations, because if you don't understand the concepts, the equations become a little bit meaningless. Okay. All right, so let's just kind of get back to this idea of energy conservation we talked about briefly in the previous recording. So whenever there's some kind of interaction that happens, we can measure how much energy was transferred, whether it was added or removed. And we call that change in energy. Mathematically, we write it with this capital Greek letter delta. This delta just means change. So whenever you see a delta E, E for energy, that describes change of energy. And conservation of energy tells us energy cannot be created or destroyed, simply converted from one form to another, or from one location to another. So it's what we will focus on really is these, not just how much energy your system has, but more importantly, how does the energy of the system change? So as you will see, conceptually, there's going to be a huge difference between writing down delta E versus just E. So whenever there's a delta E, that means energy is changing. There's some kind of interaction that's causing that change in energy. So if energy of an object increases, something else must have given that energy. So something else must have lost that energy. So in the previous recorded, we always talked about it in terms of, well, you add energy, so the energy of the object must increase. But then that other object that added the energy must have lost that energy too. So we can define kind of our physical system to contain everything, the environment where that energy comes from and the actual object of interest. And we can think about energy conservation as it's leaving one object and entering another object. And vice versa is true. If it decreases, then that energy has to increase somewhere else. Now, how is this energy transferred? And this is going to be an important distinction. So there's different ways to transfer energy. One is from what we call heat. And heat has to do with energy being transferred only due to a temperature difference between two objects. So when you put a hot object, when you mix it with a cold object, you put a piece of ice outside on a hot day, why does the ice melt? Because there's a temperature difference, there's an interaction between the ice and the hot air. And it's that temperature difference that causes that interaction or causes that transfer of energy. So heat, whenever you have a transfer of energy due to heat, it must come from a temperature difference. Everything else, all other kind of energy transfer will be due to what we will call work. We will look at work in more detail in a couple of lectures when we start looking at more mechanical systems. And work has to do with force. So how do you get an object moving? If there's, if you have a box sitting on your floor, which is stationary, how do you get to move? You have to apply a force. You have to push it. And then when that object moves, it gains energy. We'll give that energy a name. It will be called kinetic energy. It's not really important right now. The point is it's a different way that we have transferred energy. We have done work on that box, which will be associated with a force, and we've given that box energy. So there's two different types of energy transfer we'll focus on. In the beginning, for now, we will mostly focus on just heat. So this course is about energy, how it's transferred, and how it's conserved. So this slide kind of contains a lot of the meat of the course. Okay, let's now take all these words and put it into an equation. So this is kind of the statement of energy conservation. So if we define some physical system and we observe that the total energy, and the word total will be important because that physical system might have various changes of energy. It could be thermal, it could be bond, it could be other forms of energy. So the total energy of that system, if there is a change, that change has to equal to the heat that was added or removed plus the work. So if there was both heat involved and work, then both terms will be relevant. In the beginning of the course, at least, we will either look at systems when there's just heat or just work. Towards the end of the course, we will look at both when we look at thermodynamics. So for now, at least, we will mostly focus on heat. In the next couple of weeks, it'll be work, and then we'll kind of combine the two concepts. So on the left side of the equation describes the change in the total energy of the physical system, and the right side of the equation describes that ways to transfer that energy, either through heat or work. So it's kind of a really simple equation, but again, as we will progress through this course, you'll see how powerful this equation is. Okay, let's summarize what we have learned so far. So here's the types of energies, and here are the indicators, the things that tells us how these types of energies changes. So we've talked about thermal energy. We often simplify it by writing E sub TH, or you could write out thermal, but this is kind of what you will see most commonly. And how do we know when thermal energy changes? When temperature changes. So that's the indicator of temperature. When temperature increases, so does thermal energy, and vice versa. Then we also looked at bond energy, which we indicated, we write it like this, E sub B, or bond is fine too. How do we know when bond energy changes? Well, we saw two examples, either when there's a phase change, So the indicator is then the mass of the substance that went through a phase change. So for example, if the mass of the liquid phase is increasing, then we know that the object is melting. So then the bond energy will be increasing as well, and vice versa. We also looked at bond energy in terms of chemical reactions, and the indicator that's more common when we talk about chemical reaction is number of moles. So we normally don't describe chemical reactions in terms of the amount of mass that change in a particular molecule, but rather the number of moles. So you will see that normally moles is what we'll use to describe chemical reactions. So if there are 2 moles that were formed for a given substance, when we form bonds, that's when bond energy decreases. When we break bonds, it increases. There are other forms, so this table will get bigger as we move on. So for now, it's not relevant at this stage, but there will be other energies that we will introduce later in 7A, such as kinetic energy that I already briefly measured, and then this other new type of energy are called potential energy, and we'll see some different examples of potential energy later in the course. All right, so let's get back to our 3-phase model, and let's focus specifically on process A and how can we use energy conservation to now kind of more mathematically describe what's happening in the process A. So in general, whenever you're given a certain process to work with, there's some important things to answer first before you can start applying energy conservation, which we'll do next. So for example, what is a physical system? It's very important to describe the physical system. So for example, if we're looking at that process A from the previous slide, where a piece of ice is warming up. So we could just describe the ice as our physical system and just think about, okay, some energy from the outside is being added. But let's say that the source of this ice warming up is that you put it in a bucket of warm water. So maybe in a case like this, you also want to think about how the temperature or the properties of that water is changing. So we will see examples where we'll define our physical system to contain more than one object. So in this example would be the water in the bucket plus the ice. How is their total energy changing and so on? So that's kind of your first task, define the physical system. Then also the interval is important because how your energy changes depends on how far are you looking into that interaction. So for example, going back to process A, the interval could be from -30 to 0, well, which is how we defined all of process A. But maybe you just want to look at how much energy was required to go from -30 to -20. So that's a shorter interval. Or maybe you want to include a larger interval where you think about your ice becoming water at 100 degrees Celsius. So look at all these processes. So the interval just literally means the time interval over which that interaction is happening. Sometimes the interval will have a natural ending. So we will again look at this in more detail later, but when we discuss thermal equilibrium, which means when our system becomes the same temperature as the environment with which it's interacting, once thermal equilibrium is reached, there's no more temperature difference, there's no more heat being exchanged, so then there's no more interaction. So that would be kind of a natural end of our interval, but in this case, we just might want to ask a question, how much energy is required to go from one point along here to the next? So that would be the definition of our interval. Another concept that's important is the idea of our system being open or closed. So it doesn't necessarily mean, is the room open or closed? What it means, what it literally means here is it interacting with anything else. So for example, going back to process A, if we're just looking at this piece of ice and we see that its temperature is increasing, it must be interacting with something else. That energy has to be flowing from the outside. And that's what's defined as an open system. A closed system, on the other hand, is if we just threw this piece of ice in some thermal container with warm water and closed it, we can assume within a certain interval that our ice and water as one physical system is not interacting with anything else. So all the energy transfer is just happening within that system. We can ignore, let's say, if we're only looking at, 1 hour and it's, pretty well insulated container, we can ignore any interaction with the environment. And we could just focus on the interaction of that physical system, which is our ice and warm water or lemonade. And in that case, we can call it a closed system. So closed system means not interacting with anything else. And what we will do is we will kind of describe this or depict all of this using energy interaction diagrams. And you will see in some examples I'll give next that an open system, how you will depict it is by drawing a big circle around your whole physical system, which is dashed. So dashed, things can get in. When it's a solid line, it will represent a closed system. Then you have to think about what are the energy, so this word systems just means, energy types that are involved. Do we have thermal energy? Do we have bond energy that's changing in that particular interval? So if we're looking at just process A, we know that that's thermal energy. Our whole interval contains, we're going from minus 30 degrees Celsius to up here, let's say 100 degrees Celsius, and we have thermal energy, we have bond energy, and then we have thermal energy again. So you have to think about in that interval, what energies are involved. So these are the decisions you have to make before you can write down that energy conservation diagram. And then you actually, once you kind of think about your process, then you can draw that diagram. And here are just some instructions on how to draw it, but it's best to just move on and show you an example. And then finally, once you have your diagram, you will write down conservation of energy equation. So these diagrams that you will be drawing, known as the energy interaction diagrams, their main purpose will be to really help you put all these ideas together in order to write down the energy conservation of energy equation. So that's kind of the main goal here. The actual diagrams are just a visual aid to help you put all the ideas together. All right, so let's look at that process A. We have ice that starts at minus 30 degrees Celsius, and we go to 0 degrees Celsius. So what is our physical system? We don't know where that energy is coming from. That's all we're given. So the only thing we can really include our physical system is that ice, or H2O in the solid phase, kind of more formally written. What's the interval? Well, you're given here that interval. We start at minus 30, we go to 0. So we know the physical system, it's ice. So this is an example of this energy interaction diagram. Inside the bigger circle, what you will draw is all the possible energies that are changing. In this simple process A, all we have is a thermal energy. If we went all the way to, let's say, 0 degrees water, that means we also went through a phase transition. So you would have another circle inside here for the bond energy. But here, for that interval of going from minus 30 ice to 0 ice, we only have thermal energy. So you write in that little circle the energy that's changing. In which direction is it changing? Well, we know its indicator is temperature. We know temperature is increasing, so it's going up, which means that thermal energy is going up. And then below, again, just to keep track of things, you write down exactly the range of that indicator's change. So from minus 30 to 0, the dashed line shows us it's an open system. How do we know it's an open system? Well, we see that inside the physical, so the energy of our physical system has changed, it has increased. That change had to come from somewhere. Otherwise, we're not abiding by conservation of energy. How did it have to come from somewhere? Well, because energy increases, that increased of the physical system, that energy had to be added. So this is how we indicate that. We draw an arrow going into the physical system, and Q stands for heat, because for now we're just focusing on energy transfer due to heat. And then finally, we are ready to write down, we use this diagram to write down our conservation of energy. Everything that goes on the left, conservation of energy equation, everything that goes on the left-hand side of the equation, it's what's inside here. So all the energies that have changed, and here's just thermal energy. What goes on the right-hand side of the equation is the heat, the energy transfer that either went in or went out. In this case, it went in. So it equals to Q. Q itself, we always write a plus Q here, but Q could be positive or negative. In this case, we know that thermal energy increased. So one thing that you should always do once you have your energy conservation equation written is to check the signs, make sure the signs make sense. So we know that thermal energy had to go up, so this is positive. That tells us that heat has to be positive. Positive heat just means that the heat was added, so the arrow is in. If for some reason, you draw this and you see that the arrow is going the other way around, but then everything on your left-hand side of the equation is positive, then there's something not consistent. So it's a good way to make sure everything is consistent, the diagram and the equation. Okay, so this is just starting. It's kind of a simple process, but it's good to start here, because as these processes become more complicated, you will have more circles inside here. It's good to really understand all these points in order to keep track, especially of the science. Is everything consistent with heat going in and all the energies that are changing inside? Are they increasing or decreasing, and so on? All right, so now we will take a look at an example of a closed physical system. So in this case, imagine that we have some ice and water, which is mixed in an insulated container. And initially, both the ice and the water at different temperatures. So there's going to be a heat transfer between the ice and the water, but not with anything else. That's the idea of the insulated container. So whenever you see things like that, closed or insulated container, that's sort of a message saying that we assume that everything inside that container is not interacting with outside environment and is therefore a closed system. So what is our interval? We have a piece of ice which is initially at 0 degrees Celsius, and in this interaction, all of the ice melts. It all turns into water, but the final temperature is still 0 degrees Celsius. Now the water is initially at 25 degrees Celsius, and then that water then cooled down to 0 degrees Celsius. So our final temperature is the same. Our system has reached thermal equilibrium, but initially we started at two different temperatures. So to start writing your energy interaction diagram, you write out your physical system. It has, although they're both water or both H2O, they're two separate objects, because initially they're separate, they were at different temperatures. So we have the solid phase of H2O, so a piece of ice, and then our room temperature water, and that's the interval. You want to write your initial state. We have ice at 0 degrees Celsius and then water at 25 degrees Celsius, and our final state is both things are at 0 degrees Celsius, and we have all liquid at the end. So how do we draw this? Well, let's decide first what energies are involved here. Our water here just decreased in temperature. So that's a thermal energy changed. What happened to our ice? Our ice just went through a phase transition. That's associated with bond energy. So we have ice going through a bond energy change. Is that bond energy increasing or decreasing? Well, it's going from solid to liquid, we're adding energy, we're breaking bonds. The mass of the liquid phase is increasing, so the bond energy is increasing too. And here you want to kind of describe the interval. So went from all ice to all liquid. In some cases, you will see maybe you and your thermal equilibrium is reached when 25% of your ice has melted. So that's what you would write, 25%, or how many grams of ice melted and so on. For our water, the temperature decreased, so the thermal energy went down from 25 to 0. Now notice that we draw a closed circle now around our physical system. It's a closed system, which means there's no heat entering or leaving, so there's no Q. So how do we write this in terms of our energy conservation? Well, now, because it's a closed system, so whenever you have a closed system, the right-hand side of the equation has to be 0 because there's no energy transfer. What goes on the left-hand side of the equation is now all the changes in energy. So note that for a closed system, you have to have at least two energies changing, right? Because you can't have an energy change and that change equal to 0 unless, there's really no interaction. So what we see here is we have a change in bond energy of ice. That's referring to this part of our diagram. That's a positive change because bond energy went up. Then we have the change of thermal energy of water. So right here, that's associated with this part of the diagram. So you want to make sure you label everything so you know which energy goes with what. So change in thermal energy of water. That's a decrease in energy. Temperature went down, thermal energy went down. So that's a negative sign. So it actually makes sense. One increased, one decreased, and that can add up to 0. If you have both of them increasing, then you know that there's some inconsistency there because you can't have two positive numbers adding up to 0. So you never have a closed system. That means something is gaining energy and something else must be losing energy. That transfer of energy is within the system. You never draw Q between within the system. You only think about heat when it's outside the system, either leaving or entering. But there is heat transfer, which is happening within our physical system. So what we conclude here is the amount of energy that the ice gained when it went through phase transition exactly is equal and opposite to the amount of energy that the water lost as it cooled down. So they have the same magnitude, but different signs. So again, this is an example of a closed system energy interaction diagram. In the next recordings, what we're gonna do is we're gonna go a step farther and actually figure out more numerically what does that mean exactly. What is, if you think about it, this has to depend on how much ice you put in there. How, if you put 1 kilogram of ice but not so much water, would you be able to, what would be the final equilibrium state? Or if you had a lot of water but a little bit of ice, you might not end up at 0. So you'll actually figure out based on the amount of substances you have, their initial temperatures, how do we figure out what's the equilibrium state? So we're gonna kind of take these a step farther and describe like thermal energy and bond energy in terms of mass and the physical properties of your substance. But again, right now we're just kind of putting the pieces together one step at a time. Okay, so let's again summarize. So the goal of the energy interaction diagram at the end is just to write down our energy conservation equation. But it's a tool that helps us do that. And there's certain questions that we need to ask ourselves before we can jump into writing down this equation. What is the physical system? That will help us figure out, which energies are involved. What is the interval? What's our starting and ending indicators of thermal and bond energy and so on. Is the system closed and open? What are the energies involved? Do we have thermal energy? Do we have bond energy? Do we have both? And we draw the diagram, and then that diagram will help us write down the equation, and you can kind of check for consistency and signs to make sure that it may physically make sense. All right, so let me ask you kind of a question so you can think about it a little bit and practice these ideas of energy conservation and using these diagrams to help you understand it. Okay, so here's an example of an energy interaction diagram. And in this case, suppose we have a system where 100 joules, so joules is units of energy, as we will see shortly. So 100 joules of energy as heat comes in from the outside. And then I claim that the only energy of the system that changes is this energy that we call EA. It could be anything. And that EA decreases. So this is my claim. So we have only one energy changed and a decrease. So can I be correct? Yes, it's possible that I'm correct. Yes, I'm definitely correct. No way I'm correct. Okay, so think about what this tells you about how energy is being transferred, how you can translate this diagram into energy conservation. Pause the video, think about it, and then I'll explain it. Okay, so what is this telling us? Well, we know that we have added 100 joules of energy, so that's positive because heat is positive, it's going into the system. And that has to equal to the change in energy of your physical system. I'm telling you that there's only one energy that changes. Energy system just means one energy type, and that's this EA. So if we added energy, energy conservation tells us that change has to be positive. It can only go into increasing. If there were several other energies involved, that maybe perhaps something decreased, but the overall net result has to be an increase in energy. And because there's only one type, it has to increase. So this is not correct because this is showing us that EA is decreasing. So it's not possible. It does not abide by conservation of energy. So there's no way that I can be correct. This diagram just doesn't make sense. It goes against conservation of energy. All right, so that's it for this recording. I will see you next time. And again, as I mentioned, we will go into more details about exactly how to connect things like thermal and bond energy to the amount of substance you have and the type of substance you have and what type of phase transition, let's say, you're going through. Are you melting, vaporizing, and so on. See you soon. Bye.